Okay, let's get started. Okay, so in the last lecture, we continue talking about the proof of the channel coding theorem, right? So first we finished talking about the direct part, which is the achievability part, right? So for this part, we have like 3 major steps. The first one is to define, what is coding, what is decoding, and so on, right? So basically, we use the idea of random coding, right? So that's very, very important. So yeah, the random coding is a very extremely important technique for the achievability part in information theory. Okay, so later on, so we're going to use that a lot. And then we compute the expected average error probability, right? So, and then here the key part here is to use the typicality decoding, right? And also you use the union bound to characterize this error probability, right? So basically we can show that, what we can show is that when n goes infinity, then this error probability will go to 0, okay? And lastly but not least, so we need to convert the expected average error probability to the maximum error probability, right? So there are 2 steps here. First step is to convert from expected average error probability to what? The average error probability, right? Get rid of the expectation, okay? So that part is easy because if the average expected error probability goes to 0, then at least there's one code such that the error has to go 0, okay? So that part is easy. And for the other part, convert from average error probability to the maximum error probability. So that's kind of tricky, right? So we use a technique called expurgation. Okay, so basically we keep the first half the best half of the code, okay, and ignore the worst half of the code, the worst half of the code, right? And then showing that, okay, for the best part, the best half of the code, then we can show that the maximum error will be less than 4 epsilon, given the average is less than 2 epsilon, right? And then, okay, we say, okay, we sacrifice the rate a little bit, but actually, this doesn't count a lot, right? Only like 1, okay? So we're okay, right? So this idea for the converse, for the direct part, and we start talking a little bit on the converse part, right? So basically, yeah, for the converse part. Firstly, what we argue is that, okay, so ideally what we want to do is that we want to show no code with R is bigger than C, and the arbitrary small error probability is achievable, right? But we say, okay, so, normally this is not what we do. So what we do is an equivalent statement. So basically it means that, so we can show, if there's a sequence of this Rn code, okay, and then if there exists such kind of code such that the average error probability goes to 0, and then it must be R is less than or equal to C. Okay, so that's basically what we want to show here, right? And here, so this average is, so the reason we can use the average probability here is that we assume the message is uniform distribution. Okay. All right, so, and so yeah, we start from here. So basically, yeah, so I will probably repeat the steps here, so to make it a little bit easier to argue. Okay, so today, today is our lecture EEL6532. It's our lecture 30. And today, we're going to finish about the converse part, the converse of channel coding theorem. Okay, and then we'll start talking about the 0 error capacity. So if of time, so we're going to start talking about the feedback capacity. Okay, so yeah, let's start. Let's see. Yeah, let's redo a little bit for the converse part, right? As we assume that, as we said before, we assume that the message follows a uniform distribution. Okay, so the error follows a uniform distribution, and then what we do here is that we start from NR, right? And then we can write that as h of n. So this step is because it's uniformly distributed. right, then the entropy achieves the cardinality bound, right? Yeah, and then, so this is a typical step. So basically, we have to have the mutual information part, right? So basically, what we do here is that we minus this guy, right? And this guy will be a mutual information, right? And then we have to add this back. Okay, and then, so this guy doesn't matter anymore, right? But we can write this as, so this will be less than or equal to this guy, right? And this error is the average error probability, right? So because it's uniform distribution, so we can compute that. Okay, so basically that's equal to the average, the error probability defined in the channel funnel inequality, right? So this is the funnel. Okay, great. And then we can see this guy is less than or equal to the mutual information between these two guys, and plus 1 plus the average error probability, and then times NR. Okay, and then we say, okay, so using the data processing inequality, right? So basically we can write that. So this guy is upper bounded by x n, y n, and plus 1 plus this guy. Okay, the reason of that is so this follows a Markov chain. Okay, therefore the mutual information between x and y would be bigger than or equal to mutual information between m and y, right? So the closer the better for mutual information. Okay, and from here you can see that this is a generic, right? So for any kind of system, so we can have this kind of thing, right? So we can, it doesn't specify what kind of channel we have, right? As long as, here we can have whatever channel we want. We have DMC channel, and we can have, for example, in practice, we can have our MIMO channel, for example. We can have, AWGN channel, as we learned in communication class. We can have the multiple antenna channel. It doesn't matter what kind of channel it is, right? So this is always true, okay? But what is the bad part of it is that it is not very, very useful, right? Because here we can see, so this is almost the channel capacity, right? If we let error go to infinity, we have only plus 1 here, right? And if we divide by n on both sides, this 1 will disappear, right? So basically, so this mutual information can characterize any kind of the point-to-point channel capacity, right? But it's not very useful because there's no way to compute it, right? Because what is n, right? When you let n goes to infinity, right? Then how can we compute, when this n goes to infinity and then divide by n? So this is when you compute the limit here, right? So this is normally complicated to compute. Okay, therefore we do not want that, right? And this is also not our channel capacity, right? Our channel capacity is the maximize of the mutual information between x and y, not between the mutual information of x and yn, right? Okay, so next part is extremely, extremely important. So this is called single letterization, right? So basically what we can get is that we need a single letter or simplified notation here, right? So we do not want this. So we need to simplify that, right? So now let's see how we can simplify that, right? So this basically, we can write it. And we have two ways to expand it, right? So in this case, we need to expand it in this way. You can also try the other way, okay? But well, that may not work, okay? So basically here, what we do is as follows. So yeah, so remember our goal, okay? So our goal is to do the single letterization, right? So this part is not difficult to get, right? We just, we can have a very easy upper bound of it, right? But for this part, it might be tricky, okay? So conditional entropy, right? And if we have to expand it in this way. Okay, this is basically the chain rule. There's nothing new here, right? But we need to do it in this way, okay? So the reason we want to do in this way is that we have an important property of the channel that we have not used before, which is the discrete memoryless channel. Okay, remember what's the definition of discrete memoryless channel, right? The probability distribution, the conditional probability distribution of yn given xn will equals to, the product of p y given x, right? Okay, and because of that, we need this kind of form to use that. Okay, then therefore use the DMC property of the channel, right? You can see that all the history, given basically from here, given xi, for yi, it only depends on xi. It does not depend on anything else, right? That's by definition of the DMC channel. Okay, so basically from here we can get this equals to this. Okay, so this is by definition of the DMC channel. Okay, so it's memoryless channel. Okay, and then for the first term, it's easy to compute, right? We can have a easy upper bound of it. Right. So one thing we need to be a bit more careful here is that so the channel is DMC, right? So yi only depends on xi, or given xi, so all the yi's are independent, okay? But does that mean all the yi's are independent anyway? Not really. So given xi, all yi's are independent, but without given x, so yi can be dependent. Okay, therefore we have upper bound here. Okay, not strictly equal, right? And then, so this is what we get, and here we can combine these two, right? So basically, that is this y given xi, and this will provide us mutual information between xi and yi. Okay, and then, so this equals to this. Okay, and we're almost done, right? So by definition, right, what is capacity definition, right? Capacity means the maximization of the mutual information over px, right? Clearly, this guy, so this guy would be less than or equal to NC. Okay, and together with what we derived from here before, right? So then we can conclude that NR will be less than or equal to NC plus 1 plus P bar N NR. Right, and then, so R will be less than C plus 1 over N plus PEN times R. Okay, clearly let N goes to infinity, so P will go to 0. That's by definition, by requirement, right? And this guy also goes to 0. Okay, and then therefore we show the capacity R has to be less than or equal to C. Okay, is that clear? So this is how we show the upper bound, the converse. Okay. Now let's summarize a little bit. Okay, so let's see how can we do this, right? The first step is that we need to connect NR to the entropy, right? So this is the first step, like what we did in the source coding, right? Very similar steps here. Okay, so first step we need to connect the rate to the entropy, right? Here the reason we can write equal is basically because M is uniformly distributed, right? If M is not uniformly distributed, we have a we have a lower bound here, right? This guy will be bigger than or equal to HM, which is not what we want. We want less than, right? Therefore, we have to do this assumption. Okay, this is the first step. And this is the second step. So second step, we need to add a minus term and then add it back to have a mutual information term. Okay, we'll always do that, right? So this is the second step. Okay, and the third step is to use Fano. Okay, to have this kind of thing. So this is the third step. Okay. Third step, Fano. And fourth step is to use the data processing inequality. Okay. And the fifth step is to do the singularization. Okay. And this is the fifth step. Okay, 5 steps to prove the channel capacity. Okay, so now you should just close your nose and think a little bit more, right? What are the steps here? Okay, and later on probably we're gonna see one or more examples that we're going to use this technique again. Okay, so this is more or less true for all kinds of converse proof. Okay, sometimes easy, sometimes not. Yes.
Can you explain again where we were saying how the yi, like the yn is independent, but like the yi's like together like are dependent on each other?
Yeah, you can have some example here. So basically, So what we mean here is that, let me use a different color. So this, let me see. So the definition is this guy has to be equals to, oh, I read it in the reverse. Yeah, I should. Yn given xn equals to xi given yi. Oh no. Yi given xi, right? So this is a basic definition, right? So basically means that given x, all the y's are independent, right? But it doesn't mean all the yi. So basically, it doesn't mean. So this cannot. We cannot derive this. Yeah, this is simply not true. Okay, so you cannot show it. So one thing we need to be a bit careful here is that, in addition, so now let's say, so this is the error probability lower bound, right? So it's so because we have this, right? So we can have a lower bound for our error probability, right? So P bar. So that's equal to 1 minus C over R minus 1 over NR. Okay, and here, clearly from here, we can see that, so if R is bigger than C, right? So if this guy is bigger than the denominator, is bigger than the numerator, okay? And then this guy is always a positive number, right? So this guy is always bigger than 0 for all n, okay? Then that conflicts with our requirement, right? Therefore, so R bigger than C is not possible, right? So that comes back to our original argument, right? So if we say here, so, oh, it's in the last lecture notes. Yeah, so our original argument is that, so for, so R, if R is bigger than C, so we cannot find any code that has some vanishing error probability, okay? So we're good on this. Okay, great. So next, let's take a look at the zero error code. So we kind of see this before, right? Because normally, let's say if you assume the noise happen everywhere, right? Then it basically means that we may have to have an error anyway, right? The error probability can go to 0, but we may need to have an error anyway. Right, but under some circumstances, it's possible that there's no zero, absolute zero error. Okay, so first of all, let's see a definition of it. So the definition of zero error codes is that if for all m in our message set, okay, and then our error probability for any message is goes to 0. Okay, and then we say that the code is a zero error code, okay? Yeah. So basically, if the error is 0, then we say it's zero error code, okay? So can you give me an example of zero error code? So kind of seen that before. Right, do you remember that? So we're just starting talking about the channel coding. So we'll give an example of the noisy typewriter. Okay, so for noise typewriter, basically if we type a letter, then there's a positive probability that it goes to another letter, right? So basically now let's consider this example. Let's say if we have 0, 1, 2 until 3, 4. We have 5 letters, right? And then we say, okay, so if it's 0, then when we type it, we have some chance to go from 0 to 0, and also some chance from 0 to 1, okay? Or let's say if I have a 1, we we do something like that, right? So, and if I have 2, then we can do this. Okay, and say if I have 3, we can do this. And similarly for 4, right? For 4 is a bit tricky, right? We have to go back to make it symmetric, right? So this is a noise typewriter, right? So basically now we can see that. So for like maybe we'll assume some probability here, half, and so on. Everything's half, right? So basically you can see that if we type a 0, then we can go to 0 or 1. If there's a 2, we can go 2, 1, 3, right? Okay, what does that tell you? Right, it is possible to have a 0 error, right? Because if we type 1, so those are the only possibilities, right? And if I have 2, right? So let's say 1, those are only possibilities, and 2, those are only possibilities, right? Okay, so let's say if you only transmit 0 and 2, right? Then we can transmit, 2 symbols, right? In this way, so we're not going to have any error, right? Now, if in this case, so we design our code book. So C, in our code book, we have only 0 and 2. Let's say here we only use 1 digit, meaning the length of the code is 1. Okay? So our code book is 0 and 2, right? So we only transmit 0 and 2. Okay? And then what is our rate here? Remember, rate is log of m, right? The size of our code book, right? So 1 over n, of course, right? But n is 1, so basically this is this guy. So that's log 2, that's it, 1 bit, right? So we can transmit 1 bit, which is not surprising, right? So basically every time we can only transmit, we have only 2 symbols here, either 0 or 2, right? Any questions? So those are the 0 error code, okay? But you can see that, the fundamental reason that we could have 0 error code is that, the noise is very limited, right? If we transmit 0, it can happen only 0 and 1, so it cannot have 2, 3, 4, right? But if we can, then there's no way to have 0 error code, okay? Okay, another thing, another observation here is that, so from what we proved before, right? So we can see that we have to let n becomes large, right? Then what is the benefit of it? Right now, n is just 1, right? So why we want n to be large, right? Why n is larger, that is beneficial. So basically means that we have a higher capacity, meaning that we can transmit more bits, right? More than 1 bit per, n, per channel use. Okay, so if we're not really clear on that, we can just try it, right, and see what we can get, right? So basically now, so we try the case where n is 2, right? So now we have to have a matrix, right? So we have to have, let's say, the first symbol is 0, 1, 2, 3, 4, and second symbol is 0, 1, 2, 3, 4, right? So if n is 2, the first symbol could be 0, 0, 0, 1, 0, 2, 0, 4, 3, 0, 4, or 1, 2, 1, 1, whatever, right? We just try it, right? So for example, now let's say, we can have a grid here to make our life a bit easier to present. So if I have a grid here, okay, let's say we transmit 0 and 0, okay? We just do 0 and 0, okay? We transmit 0 and 0. Right, then we need to see what are the possibilities, right? And then we cannot put any code word there, right? For example, in this case, if 0 becomes 0 or 1, we cannot use 1 here because 1 can be in error, right? So here, let's say if we want to transmit 0, 0 here, right? Let's see what are the possibilities, right? So if transmit 0, 0, and then what are the results? Could be 0, 0, right? And could be 0, 1. Right? Could be 1, 0. Oh, we don't need to. And could be 1, 1, right? Right? It basically means that we cannot, if I want to use 0, 0, we cannot use 0, 1, 1, 0, 1, 1, right? So basically it means that, so those 4 squares, okay. If you think, this is kind of like the typical set, right, given X. Okay, and based on this idea, you can try all, now, if I transmit 0, 0, and then these 3 can now transmit, okay? It's a hard no, right? And then we can keep doing this, right? Eventually, I'm not going to do it here, but you can verify that at home. So we can use this letter, this letter, this letter, and this letter, okay, without any error. Okay, so we can transmit 5 basically over 2 symbols, right? Then what is the rate? So in this case, our code book is 0, 0, 1, 2, 2, 4, 3, 1, and 4, 3, okay? And in this case, so our rate is 1 over n, which is 1 over 2 log 2, and there are 5 symbols here, right? 5 code words. Okay, so this would be the rate, right? So clearly this is bigger than 1, right? Because if it's 4, then it's 1, right? So it's 5. So, and then as n increase, so we can transmit more. Okay, so this basically means that we can transmit this number of bits over 2 channel uses. That clear? Okay, so yeah, if we do this, use more. Basically, it means that that intuitively the idea is that we introduce correlation in the code word, right? The code words are related, right? So they are not independent, right? Because for example, if the first one is 0, the second one has to be 0. Okay, it's not independent, right? We increase the correlation among the code word, right? Then we can carry more information over them. Okay, so now we have a theorem. So this is kind of an obvious one, right? Then what is the 0 error capacity, right? So let C naught be the highest possible rate of a 0 error code. Then the 0 error capacity C naught will be less than or equal to C, right? Because C is the more relaxed version, right? Allow you some 0, right? But for 0 error, of course, you cannot beat it. And so the proof of it, I'll give you, you can do it at home. So that will be exactly for the step we just talked about. Okay, because yeah, I think the only thing you need to be more careful here, not be more careful, it's simpler here is that because it's 0 error, right, given yn, and the entropy of m given yn, so that will be what? So you don't use funnel there, right? Because use funnel there, then you let this error code become 0. You say this is less than 1, but you don't need to do that, right? Because it's 0 error code. If you know yn, you have to know m. Otherwise, it's not 0 error. Therefore, this entropy goes to 0, becomes 0, right? Then it just follow everything else. That'll work. Okay, so basically that'll be the idea. Okay, next we need to talk a little bit more on this feedback channel capacity. So this is very interesting, right? So now let's consider a different channel, right? Before, what we consider is that we have an input message m, right? So that's our message, right? And then we have a channel encoder, right? We assume the m is uniformly distributed, of course, here, right? Later, we're going to relax that condition, okay? And then we can have a DMC channel, right? Assume it's our DMC channel, right? And then we have a decoder. And then we have our m hat, and so this is our estimate. Okay, and then we're good, right? But here, let's say, okay, so at this moment, before our decoder, so we denote that as yi. Let's say if we transmit xi here, okay? So the decoder, before the decoder, so this receive, right? It basically means that when the receiver receives yi, so it can feed it back to the encoder. So basically it tells the encoder what I got, Okay, and we assume there's a one-step delay there. Okay, this D means delay, one-step delay. Okay, so in other words, basically means that when we do the encoding, so before we only need to know the message. But now, besides the message, we also know the feedback information, right? So if we're transmitting xi now, so basically all the message in the past will be fed back. Then we know all of them. So it's a vector of yi minus 1. Okay, so basically use all the previous fed back information to encode the message n. Okay. Does that make sense? Right, so basically it means that, let's say if this is time slot, so in the first time slot, let's say, okay, we have an encoder function f1. So that's to encode, at the first time slot, there's no feedback, right? So then we encode the message from m to x, right? And x1 is basically equals to f1 of m, right? And then in the second time slot, let's say we have another encoding function here, right? And then we do, so then the message would be m and the y, and then we encode that as a code word, and the x2 here equals to f2 m of y1, right, and so on, right? So basically, if we have the nth time slot, we have fn here, so that's basically m of yn minus 1 to xn equals to fn m, and all the y's, y1, y2 up to yn minus 1. We use all of the information to encode. Is that clear? Okay, great. So basically, yeah, so I ignore, the definition, you know what we mean here, right? So basically, and we still consider the fixed coding. What? Oh, okay. I see. I need to move a page. Yeah, why I have a new page in front? Yeah, I can adjust that later. Okay, no problem. So, okay, yeah, maybe I'll just write down one definition here, and everything else will be followed before. So here we still consider a block code. Okay, we consider an Rn code. So basically means rate R and the length is n, right? Fixed length block code with feedback is defined by a sequence of encoding functions. Okay, so because the input are different, right? So now we have a number of encoding functions like this, right? And I is from 1 to n such that xi equals to fi x y1 till y minus 1, right? So this is the encoding function, and everything else will be the same as before. Everything else is defined the same as before. Okay, very good. Okay, so now the question is, so we can define the same capacity, right? So basically, yeah, let's define the capacity here. So basically, the feedback channel capacity so we call this CFB feedback, right? So that's a supremum of all R such that R is achievable. Okay, so that'll be it. Yeah, so this model, you can see that, so this may be kind of an idealized channel, right? For example, in practice, so ARQ is protocol can be considered one example of such kind of channel. So ARQ it means automated repetition request. You heard of it in communication? So it's called automated repetition request. Q is here. Right, so basically, it means that the receiver will tell the transmitter whether you are successful or not, right? So that is used in the upper layer communication, maybe in the second layer, so a bit upper layer communication, so not exactly the physical layer, right? So this is the ARQ. So we're going to see this a little bit later, okay? So now, clearly, so we can see from the input here, so besides X, we have more information, right? So it is possible that we do not use any of those Y to encode, right? Therefore, we can, so obviously, the CFB will be bigger than or equal to C, right? The feedback capacity has to be bigger than or equal to the capacity without the feedback, right? Because we have the option to not use the feedback. That makes sense? Okay, so now the question is, so whether it can be larger than the capacity without feedback, right? Meaning, so is feedback useful or not? Right? What do you think? Do you think feedback is useful? Yeah, think about what we are doing in wireless communication or in whatever communication system you are using, right? Do we use feedback, right? If we use, it means that it's useful somehow, right? If we don't use it, it probably is not useful, right? Do we use it? Or do you think it's useful, the feedback? Yeah, who think is CFB is bigger than C?
I don't know if it would always be bigger than.
That's great. Yes, and yeah, let me give you more constraint here, right? So now we're considering a point-to-point discrete memoryless channel, right? In this case, is that going to be useful or not? Yeah, probably that's not a good question to ask anyway, right? You think it's not, it may not be useful?
I don't think so.
Why?
I mean, it's memoryless, so there's really no relationship between successive samples you receive and stuff.
Yeah, that's the right intuition. Yeah, so basically, yes, memoryless. So basically, things are independent. Yeah, that's the intuitive reason why it may not be useful. Okay, so, but yeah, let me write down the theorem first. The feedback capacity of DMC is given by, so CFB equal to C, right? Meaning, Okay, so basically, in terms of capacity, it is not useful, right? But, that's not the answer I expected from you, right? As we talked about before, ARQ is used everywhere, right? That's why we have this protocol, okay? And for example, in wireless communication, so let's say, for 5G or Wi-Fi, so we have this multiple antenna system, right? So we always fed back the channel state information. Feedback is, we always do that in practice, okay? And then if it's not useful, why we want to do it, right? There's some clarification here. So I would not say, feedback is not useful, right? So people really do not like this statement, and people consider, you misunderstood Shannon, right? He doesn't mean that. Okay, there are a few, things to be clarified, right? So this is like, just a purely mathematical impact, right? First of all, in order to show this theorem, we need to let n goes to infinity, right? If n is not infinity, then we don't know, okay? So the rate, for different codes with feedback or without feedback, the rate to achieve the capacity may be different, first of all, right? It's not a finite end result. It's a, infinite end asymptotic result, okay? And the other thing is that, so yeah, this result is no longer true if the channel has memory, okay? Not true if channel has memory. In that case, the channel with feedback may achieve a bit higher capacity, okay? And so this is now true for a multi-user system, multi-user channels. Okay, and feedback can achieve much larger capacity. Okay, for example, let's say we consider a multiple access channel, right? Let's say our computer and our phone talk to the Wi-Fi access point at the same time, right? If I have feedback, then we can achieve higher capacity. Okay, so yeah, feedback can be useful. So yeah, and the other thing is that, so although feedback does not increase the capacity into this one-to-one memoryless channel, but it can simplify our design a lot if we have feedback. Can simplify our design for point-to-point DMC. Okay, so therefore we can achieve a better complexity, for example, right? Let me see an example that about ARQ, so to see why it's kind of useful, right? So yeah, let's consider the BEC channel, binary erasure channel, and we consider ARQ protocol. Okay, so basically, let's remember that binary erasure channel means that for the input alphabet, we have 0, 1. For the output alphabet, we have 0 and 1 and error. Okay, and then, so this is what we get. So something like this, right? 0 and 1, 0, error, 1. Okay, and then we have some error probability going on here, right? So there's 1 minus epsilon, here epsilon, 1 minus epsilon, for example. Okay, and now let's assume for ARQ, so what we do is that we do not feedback y, but we feedback function of y. We just feedback whether it's error or not, right? If at the transmitter side, if we receive an error, we just retransmit. So that's our code. That's simple enough, right? So let's see what is the performance here, right? So basically in this case, so let's see that, let's say we have a sender here or transmitter, and we have a receiver here. And let's say we transmit 1. Okay, and then at receiver, let's say we have an error here, so that's an E. Right, then the receiver will tell the sender, okay, so it's wrong. Okay, then it will transmit 1 again. Okay, then let's say, okay, I got a 1. Oh, sorry, I got an E again, for example. Right, there's another error, and then I tell the sender, and the sender will transmit a 1 again. And then if I receive a 1, then I'll tell the sender, okay, now you're good. I'm receiving a 1. And then you will transmit the next symbol. Let's say you transmit a 0 here. And then if I receive it, a 0, okay, right? And then that means there's no error. Then I tell the transmitter again. So you can transmit a 1, for example, and so on. Okay, so this is basically, how it works. Right now, we can see that we transmit like, we only transmit 3 symbols, right? So now n is 5, but we only transmit 3 symbols. The symbols we transmit are 1, 0, 1. Okay? So we have 5 channel uses, but transmit 3 symbols. Okay, so this is ARQ. Okay, but meanwhile, it's also channel code. Okay, so now let's see the performance of channel code, right? So it's relatively easy to see the performance of it because now we know the channel distribution exactly, right? So now let's see, let's compute what is the total time or total expected time to transmit one symbol. Okay, let's say we just transmit one symbol. Right, let's assume this is an attempt, which is t. So now I want to compute the expectation of t, right? So now let's say here is a successful probability, right? Let's say if we attempt once, then what is the failure probability, or what is the successful probability? Right, remember, so this is what we're working on, right? So if we transmit something, then the successful probability is 1 minus epsilon. Right, 1 minus epsilon, right? So this is the success probability if we just use one symbol, right? And then let's say if I transmit 2 symbols, what's the successful probability? So the first time has to be failed, and the second time succeed, right? If we use third, then the first 2 times have to fail, and then the third time succeed, right? And so on, and so on, right? If you look at this distribution, so did you recognize what that is? It's like, flip a coin until we see a heads or a tails, right? So can you tell me what the distribution of t? Very good. Oh, geometric distribution with probability of epsilon, right? So now we can compute the expectation of t here, right? So that's basically equals to t from 1 to infinity and t times the successful probability, right? So that's equals to this t minus, we need to write down the pt here, right? So it's epsilon power t minus 1 minus epsilon, right? So then we can write this as 1 minus epsilon times t epsilon t minus 1, right? Then what is that? T times epsilon t minus 1. Yeah, that should be easy enough, right? You just do the integral of it, and then if you do an integral of it, then you're gonna get geometric series, right? And then do the differentiation, then you'll get, so this will be the result, okay? And then there will be this. So that's the average length, okay? But now we deviate from our definition a little bit, right? So for our definition, so we can see here that what we're working on is, where is it? Is this Rn code, right? Where n is fixed length code. Okay, but from this example, it's a little bit different from what we said before, right? So we're working on a variable length code, right? So this will result in a variable length code. Okay, variable length feedback code. Okay. But we can still compare the performance, right? So let's say, let's just compare the performance, with the fixed length code, right? So basically, if let's say we transmit NR symbols, so for each symbols we transmit with time t, okay? So now let's say in total we want to transmit this number of bits, okay? Right? So we want to transmit this number of bits, right? So basically the total time we're using, or the total number of channel uses is as follows. So it's nr times t. So this is the total number of channel uses, right? For every bit, we need t channel uses, so or the time. Okay, and that equals to nr times the expectation of t, right? So that's nr divided by this one. And remember, so if we want to transmit this number of bits using a fixed length code, right? It result will in the n channel uses, right? And this will be equals to n basically. Okay, and now we can see r will equals to 1 minus epsilon, right? Yeah, because this n and n canceled, we can see r equals to 1 minus epsilon. Magically, this equals to the feedback channel capacity. So if you remember, we derived this channel capacity before. This is the channel capacity of BEC. Okay, so the conclusion is that, okay, so if we use the feedback, right, we can design this simple code and achieving the channel capacity, although it's a variable length. Is that clear? So the feedback can be very helpful, although it does not increase the channel capacity in this case. But you can achieve that with a much easier way, yes?
So in reality, if we're transmitting over some channel and that channel introduces some probability of error, then when we're getting the feedback, don't we have to get the feedback over the same channel, which also introduces
Very good question. Very good question. No. Yeah, we do not assume any channel for the feedback. We assume perfect feedback. Yeah, if there's some error for the feedback, then there's another story. Very good. Yeah, we have. Yeah, for example, we can imagine there's a wire line here for the feedback channel, and the other thing we can imagine this is that normally, for the feedback, we use a better channel. Right. One way to think about this is that, for example, did you take communication? No. Yeah, maybe. Yeah, I'll just say it, see whether it makes sense to you or not. So in communication, we use, for example, this QAM for transmission. So it's like constellation point. So each constellation point may represent a number of bits, right? For example, I say if we use 4 QAM or QPSK, so every symbol here will represent 2 bits. And you can see that, if we use this guy, then the space is pretty good, right? But I say if I use 16 QAM, something like that, you see what I'm getting, right? We cramped it a little bit with the same energy, same power, right? Then the distance between each symbol is shorter, then there's higher probability to get error, right? And then, so we use this kind of constellation to transmit data, for example. And use this kind of constellation to transmit the control signal or the feedback, right? So we can guarantee, normally we want, this very critical useful information to have a better chance to feed back. And normally this information is not as big as the data, okay? So, this is definitely oversimplified. In practice, we do not feed Y back. Yeah, we do something else, which is smaller, right? As in the ARQ example, right? So we don't feed Y back, right? We feed, just tell you whether you're good or not, right? And that's good enough, yes?
Yeah, also in implementation, there's a timeout. So if you don't get anything back, then you would just assume there's an error.
Yes.
Yeah.
Yes. Yeah, that is used in the transportation layer a lot for TCP protocol. Yeah, good. Oh, by the way, in practice, at least for a higher layer for TCP, so we don't do this. We don't do this is in the lower layer. So we don't do, okay, I transmit something, I wait for a feedback. Yeah, what if your channel is bad? I cannot get your feedback, right? So what do we do is that I just keep transmitting. And you just keep transmitting as well. And I'll see, okay, I got 1, 2, 4, 5, and didn't get 3, and then I'll transmit 3 again. Something like that. That makes sense? Okay, great. All right, thank you.